Hi everyone, so this is John. I'm going to be going over the Kinetics worksheet for this week or for this video. And so the first question we have says for this reaction, at the time when N2O5 is being consumed at that rate, what is the rate which O2 is being formed in molarity per second? So looking at this reaction, you can see that we're looking at N2O5 and O2 by the question. And all of this question is really stoichiometry, right? Because whatever rate N2O5 is being consumed at is going to be double the rate that O2 is being formed at, or O2 is being formed at half the rate at N2O5 is being consumed. Why? Because it takes 2 molecules of N2O5 to make 1 molecule of O2. So all you have to do here is some stoichiometry, is really what we're doing here. So it says that we're consuming it at a rate of -1.2 times 10 to the -4th molar. And I'm going to write this in concentration of N2O5 like that. So the molarity per second for the units. You could write the second unit on the bottom. There's a reason I'm not doing this, as you'll see in a second. Doing some stoichiometry here, we can say, well, for every -2 rate of consumption of N2O5 in molarity per second, I get +1 rate of formation of O2, or concentration of O2 per second. You'll note that these units cancel out, right? Note the -2 on the bottom, so the negatives cancel out because you are consuming N2O5, so it should be negative. And then you end up getting 6.0 times 10 to the -5th. And then this is in concentration of O2. This is molarity per second. So let's see. All right, moving on here. It says in this reaction, the concentration of the reactant changes from this to that in 85 seconds. What is the average rate of decomposition over this interval? The average rate of change is always going to be, and this is true in math and physics and chemistry, y2 minus y1 divided by x2 minus x1. So the change in y over the change in x, the change in the dependent variable divided by the change in the independent variable. So the average rate of change here, the way you can think about it, and I'm just going to write as average rate. The dependent variable is the concentration. You can think of the second one as the final concentration over this interval. Think of the first one as the initial concentration over this interval divided by the change in time, right? The concentration is a function of time, so this is okay to think of it like that. You plug these all in, right? So 0.0431 minus 0.0562 divided by 85 seconds. These are both in molarity on the top, seconds on the bottom. You get 1.54 times 10 to the -4th molarity per second. And this is negative. The answer ends up being A, right? There is no negative here, but they are saying rate of decomposition. So it's implying that the number in the answer choice is negative. Decomposing at a negative rate means you're gaining something. The reaction has a rate law of that, which will cause the rate to increase the most. So for A, the way you can do these problems is I'm going to say that this is not, or the initial rate, before we plug in some values. Now what I want to do is that doubling A is saying that in this new rate law, and I'll do 1 very explicitly, So let's say I have some new rate, the K is the same, I have some concentration of A, I'm going to call it 1, some concentration of B. Well, I know the concentration of B is the same, right? Because I'm just doubling A. I know that A is twice whatever I initially had. So when I plug this in, I get K times 2 times my initial concentration times the initial concentration of B. You can move the 2 out like this. And I forgot a square here. My bad. And then you can notice, well, this is my initial rate, right? That is the rate I have right up here. So now what you can see is that if I double A, it's twice what I originally had. So this is 2 times. Lowering the temp will decrease the rate of reaction. Tripling B, you can do the same thing here. This one was for A, this one is for C. I'm not going to write it all out explicitly this time. I'll call this rate 2. You have K. We keep A the same. For B, if you're doing it 3 times the initial concentration, you're squaring it. Make sure you put the square with the B. Otherwise, you're going to get the wrong, or with the 3, you're going to get the wrong answer if you do not do that. Right? Because you have to square the 3 and the concentration. You rearrange this a little bit. And then you can see that once again, this is the original rate. So this is 9 times the original rate. Doing the same thing with D and E. This is going to be 4 times. This is going to be 4 times because you square the 2. So these are the same process. I'm not going to do them just to keep this video a little bit shorter. Right? You would plug in 4 with the A, 2 with the B, and you end up getting C as the final answer. Moving on here, it says the reaction A plus B yields C plus D second order in A and 0 order in B. They want to know what the rate of the reaction is with those concentrations. So we're going to write our rate law. Right? When you use this rate law, rate equals some concentrations to some powers times K. It's when you're concerned with how the rate of the overall reaction occurs with respect to the concentrations of reactants. The integrated rate law tells you how one concentration, so of one reactant, varies with respect to time. So they're for different things. Keep this in mind. The rate here, we have K. You always have your K. It says it's second order in A. It's 0 order in B. B to the 0. Recall that anything to the 0 power is 1. So you're multiplying by 1, or this is K times A squared. Then you just go ahead and plug these in. 0.125 squared. Plugging this into your calculator gives you 1.9, about 1.9 times 10 to the -4th. And this is in molarity per minute. And that's it. The answer is D. Next, it says the hydroxide ion is involved in the mechanism of the following reaction, but is not consumed in the overall reaction. Um, I'm actually going to copy paste this onto another page because this is too long and there's not enough space. All right. So when you're looking at determining the order of the reaction with respect to each of these, you're really just finding the powers. Um, you're finding the powers in the rate law. So if we write our rate law, we get rate is equal to K times the concentration of OCl minus to some power. I'm just going to write A. You can use whatever you want. Really, obviously, it doesn't matter. You're just placeholder. I minus OH minus to the C. And then what you can do is, let's say I want to solve for A. What I'm going to use, or what I'm going to do, is use trials where the concentration of I and OH are the same or constant. And then plug into rate laws. And divide. So I'm going to use trials 1 and 3 for this, right? Because iodine and hydroxide are constant there. Why do we divide the two rate laws? So really what we're doing is this. Rate 1 divided by rate 2 is equal to K times OCl minus 1. I'm going to write this really explicitly once. That's to the A power, that's to the I minus, to the B power. The 1 indicates that's for the first rate, or the first trial I'm using. Doesn't mean trial 1 on this, just one trial. Any one trial. Rate 2 is indicating a separate trial, or I guess it could technically be the same one, although I don't know why you would do that. OCl minus to the A power 2. K's are the same, right? That's a constant. 2. And then we have a 2 for the hydroxide. So the reason you divide these is because given the experimental data that they give you, if you plug in to the first rate or any one rate law, right, you're going to have an equation with two unknowns. You're going to have you're going to have things, actually, sorry, any one equation, you're going to have four unknowns. You're going to have K, you don't know what K is. You're going to have A, B, and C, right? They're the respective powers of each of these things. Hydroxide's 1 in molarity, so it ends up going away, but you still have to handle with the A and the B. And you can't solve that. You can't solve one equation with three unknowns. It's not possible. So instead, what we do here is we take two equations and we divide them. Why do we divide them? Because when you divide them with certain things in mind, right, keeping certain things constant, the K's will always cancel out. The I minuses in this case will end up canceling out, right? Because they're going to be the same. I'm not going to cancel it out here since this is very general. The OHs will cancel out from what we're going to do, but it's to cancel out other things, right? So then what happens is by this division, we're getting rid of three of the unknowns, and then we just have one equation. We're left with one equation, and one unknown is what it is. So we use two equations with four unknowns, divide them to reduce it down to one equation with one unknown. So doing that for this, and I'm not going to rewrite this thing again. Just want to make it very clear. I'm going to kind of just plug in for all of these. These are all very much the same. It is a little bit tedious. I don't want to spend too much time on it since it is the same thing over and over. So using trials 1 and 3, using rate 1, that's 4.8 times 10 to the negative fourth. I'm going to leave out units just because it takes too long to write in, and it's going to get a little bit messy. So I have my two rates for trials 1 and 3. I have the K's. I have right, I haven't canceled it out formally yet. After plugging in everything, I'll do that in a second. I have OCL minus in the first trial, it's 0.004. The A power, the iodine is 0.002 to the B power. Hydroxide is 1 to the C power. You can put the decimals in. Yes, it's important for sig figs, but I'm not going to. On the bottom, we have 0.002 to the A power. The iodine and the hydroxide are the same as desired. Then these all cancel out, right? The K's on the top and bottom. 0.02 to the B power is on the top and the bottom. That turns into 1. 1 to the C divided by 1 to the C is 1. Also, 1 to the C is just 1. So those would have gone away anyways. Then when you do this, you're left with 0.004 the A, 0.002 to the A. I want to make this very clear because some people get lost in here with the algebra. This is the same as 0.004 over 0.002 to the A, right? That's just a rule of exponents. Same exponent on the top and the bottom, or if I pull it out, I can do that, removing it from the top and the bottom. And this is 2 to the A. Then we have to solve for 2. So reducing this left-hand side gives us 2, just doing the division. And then clearly A has to be equal to 1. So it's 2 to the first power is equal to 2 to the A. A can't be anything else but 1 for this equation to be true. You can use logarithms. We're going to do that in the next one. Solving for B, I'm going to keep OCl minus and the hydroxide constant. So basically what I just did for A, except the other two things, right? I'm going to keep constant. So for this, I'm going to use trials. I think it's 2 and 3. I'm going to use trials 2 and 3. So doing that, I'm just going to plug in the rates, right? Really what I'm doing is plugging in here. You can memorize the equation if you want. You are just dividing two rate laws. I think that's a much easier way to remember that. Or it's the same rate law with different things plugged in, actually. So plugging in, let's see, we have rate 1, so trial 2, that's 5 times 10 to the negative fourth divided by 2.4 times 10 to the negative fourth. We have the K's. You have the OCl minus from trial 2 is 0.002. You could write the A as 1 since we've solved for it. I'm not going to because you could solve these for in any order. I just want to make that clear that these will cancel out. You shouldn't have to plug in extra math into your calculator to solve these. They're all the same way. The iodine from trial 2 is 0.004. The B power, the hydroxide is 1. The OCl minus is the same. The iodine is halved. The hydroxide is the same, right? By what we wanted. These all cancel out. Doing our reduction on the right side, we end up getting 2 to the B power. On the left here, you end up getting something that's not exactly 2. You get 2.08 is equal to 2 to the B. You can round that down and say B is equal to 1. That's perfectly acceptable. For those of you saying, that's not okay, like how am I supposed to know? Or you really want to know the math, you could also take the ln of both sides. This would be the more mathematically acceptable way to do it, I guess. And then you can use your rule of powers for logarithms, the power rule, to bring down the b. Then you can divide both sides by ln of 2. So b is equal to ln 2.08 divided by ln of 2, which is about equal to 1. So you still get the same answer. Note, right? You're like, well, why did I divide both sides by 2? There's 3 equations here. You can ignore the middle one by the transitive property, right? ln of 2.8 is equal to this is equal to this. So ln of 2.08 has to be equal to this. If A equals B and B equals C, A has to be equal to C. So you can ignore that middle one. You're allowed to write these multiple equal signs out. That's it for that one. And then solving for C, we're going to go ahead and keep I minus or OCL minus and I minus constant. And then for this, we're going to use trials. I think it's 3 and 4. Let's use trials 3 and 4. All right, so plugging into the same thing. This is 2.4 times 10 to the negative fourth. I believe this was 4.8 times 10 to the negative fourth. Oh, 4.6. Then we have 0.002 for OCl minus and for iodine. Hydroxide is 1. On the bottom, we get the same things for iodine and OCl minus. This is 0.05 to the C. On the right side, you can cross all these out, except for the hydroxide. You get 2 to the C power. Similar thing happens here. This one is probably where you want to use logarithms more. You get 0.522 on the left side. Now, a lot of you won't know what to do with that. If you were to round down the 0.5, you could think of this as 1/2. 2 to the what power gives you 1/2. It's going to be -1. Spoiler. This is where logarithms, again, makes it very mechanical for those of you that don't want to have to worry about that, any of the mental tricks or shortcuts or just memorizing powers or whatever it is. Take the ln of both sides here. I'm just going to go ahead and apply the power rule right now. So I pulled the C out just as I did before, right? With B, I get C is equal to ln 0.522 divided by ln of 2, and this is about equal to -1. So these are all the answers for the powers. So it's 1, 1, and -1, and that's it. That's what the order is with respect to each of them. Because what is the overall reaction order? You just add the powers And you get 1. 1 plus 1 plus -1. C says write the rate equation and determine the value of the constant K. So for this one, we get rate is equal to K times the concentration of OCl minus times I minus times OH minus to the -1 power. Then you can plug in any one of these trials. I'm just going to plug in the first trial. Use any trial. I use number 1. 4.8 times 10 to the -4th is equal to K times 0.004 times 0.002 times 1 to the -1. You solve for K here, and then you get about 60. And then that is your answer. Okay, great. So that is it for that one. Moving forward, it says, so this is where we use the integrated rate laws. It says calculate the rate constant K in 1 over min for a first order reaction. That's important, with a half-life of 75 minutes. So I could go over all the derivations. I think you have all already seen these for each of the integrated rate laws. A lot of people also get lost in the calculus, so I don't think it's really worth going over. However, you can derive all of these rate constants. I think you get a formula sheet for at least all the classes I've TA'd for. Typically, you get a formula sheet. So you don't have to memorize each of the integrated rate laws and each of the half-lives in terms of K. If they don't give you the half-lives in terms of K, you can actually derive them. But I won't go over that in this video. Since you probably have it, and I don't think anyone's going to want to really see the derivation. It ends up just being a lot of algebra, is what it is, more than anything else. So it says calculate the rate constant for first order reaction. So for a first order reaction, the half-life in terms of K is ln of 2 over K. So if you want to find K, you just algebraically move this around. And then you just plug in. So it's ln of 2 divided by 75. 75 minutes. The ln of 2 is unitless. Logarithms will always be unitless. They should be. And you get 9.24 times 10 to the -3rd. And that is your answer. That's it. So very easy if you have the formula already. Next is in the first order reaction, A turns into products or decomposes into products. The concentration of A is equal to 0.816 molar initially and 0.632 molar after 16 minutes. What is the value of the rate constant K? So this is a knot for the initial concentration. We are going to use the first order equation. So this is the ln of the concentration of A. You can think of this as a function of time. It is okay to write it like this. Is equal to -K plus ln. Do I want to put, yeah, I'll put the parentheses. Of the initial concentration of A, like that. Now, what we can do is plug in all of our values. So it says after 16 minutes. You can think of this as the concentration after 16 minutes. That's ln of 0.632. We know that this is equal to -K times 16. So just like in normal function notation, if you have f of x and you want to know what f of 1 is, you plug in 1 wherever x is. It is the same thing here. I'm plugging in 16 where t is, and then plugging in the initial concentration, 0.816, get that. You do a little bit of algebra here. I need space, so I'm going to kind of skip a few steps here. You get K is equal to ln of 0.632 divided by 0.816, subtracting ln of 0.816 from both sides. Using my logarithm rules, I can condense it. You can also just plug into your calculator. You don't have to do this, but I am doing it to make this neater. Divided by -16. And then when you plug this all in, you end up getting 0.01597. And this is in units of inverse minutes, or 1/minutes. Okay. How do you know that? What are the units of K? K and T have to end up being a unitless quantity in this equation, because you have something unitless on the left, so K times T has to be unitless itself. So T's in minutes, K has to be in minutes as well, or inverse minutes to cancel that out. For B, it says, what is the half-life of this reaction? So this one's pretty straightforward. The half-life is ln of 2 over K, what we just did a second ago. And then you just plug in K. 0.01597. And then you end up getting 43.4 minutes. That's it for that one. C says, at what time will the concentration of A be equal to 0.235 molar? So for this, now what you're doing is you're plugging in 0.632 for some time t that we want to figure out. So over here, right, 0.632 is going to be the concentration at some time t. Or sorry, 0.235. My bad, I'm misspeaking here. 0.235 is going to be the concentration at some time t. So we have ln of 0.235 is equal to negative K. We know that is 0.10, sorry, 0.01, oh, come on, 0.01597 times t. That's what we want to figure out. Plus ln of 0.816. You algebraically solve for t here. I am going to skip the algebra. 0.816 divided by negative 0.01597. Plugging this all in gives you 77.9 minutes. If you're not sure where I'm getting the algebra, I would do a quick review on your logarithm rules. There's plenty of good videos on YouTube for that. I am just condensing them after the subtraction. Next, it says for D, what will A be after 2.5 hours? So now what we're doing is we're plugging in 2.5 hours for T. We do have K in minutes. K is in minutes or inverse minutes. So convert this to minutes. 2.5 hours to minutes is 150 minutes. So this is concentration of A as a function of time, right? When you plug in 150 for T, this is equal to negative K, which is 0.01597. And I am out of space. I'm gonna move that down. Do this. 0.01597 times 150 plus ln of 0.816. You do a little bit of algebra, right? You end up exponentiating both sides. So think of this as exp or e to the power of this. 0.01597 times 150 plus ln of 0.816. You could technically simplify the ln of 0.816, pull it out front. I'm not going to do that here. You just plug it in and we get 0.0744 molar. That's it. Okay. Going on, it says a reaction is 50% complete in 30 minutes. How long after its start will the reaction be 75% complete if it is first order or zero order? So in a first order reaction, the half-life is independent of time, or half-life is constant. It's independent of concentration, right? How do I know this? Because ln is a constant and k is a constant. So to go from 50% to 75%, right? You're decaying another half of the material. It's going to just be another 30 minutes. 30 minutes, right? 25% is half of 50. And you end up getting 60 minutes. However, for the zero order, it's not constant, right? The half-life for a zero order reaction is actually dependent on whatever the concentration is at the beginning of the time interval. So I guess you could technically look at this as infinitesimally small integrals. We're not going to talk about that. But we have this where k is a constant, but this is the concentration at beginning of the interval. So why does this matter, right? So for the first half, t of 1/2 is equal to whatever the initial concentration is divided by 2k, right? However, for the second half of decay, you're starting with half the initial amount. And so if I write this out, 1/2 of the initial amount, because 50% decayed, you can pull out the 1/2 out front, or it's half of the first interval, right? It takes half the time for it to decay than it did in that first half. So what this means is 30 minutes divided by 2 is 15 minutes. This is for the second half to decay. You get a total of 45 minutes. That's how you do these problems, right? Maybe it would have even been more appropriate to label these as intervals, right? T of 1/2 1, like A naught 1 for first interval and the second interval. But the half-life for a zero order is not constant. It depends on the concentration at the beginning of that interval. All right. So moving on here. Whoa, what happened? Okay. This is the first order reaction A, decomposing products, has a half-life of 150 seconds. What percent of the sample remains unreacted after 300 seconds? So it's first order. The half-life is constant from what we just saw a second ago. Um, so we can easily say, or we can easily do this. Since the half-life is constant, we can see how many seconds have elapsed divided by 150 seconds, which is the half-life. So 2 half-lives have occurred. Right? 2 half-lives, just remember you're going from 100% to 50%. Half of 50% is 25%. So the amount left is going to be 25%, and that's it for this. Going to this next question, it says the following graphs of concentration versus time of several reactions. Identify which ones are zero order, which ones are first order or second order. Calculate the value of K and the initial concentration for each reaction. So identifying these is pretty easy if you know which the integrated rate laws are, right? You know ln corresponds to a first order rate law. 1 over corresponds to a second order rate law. And then just the concentration corresponds to a 0th order rate law. So looking at each of these, A, B, C. A is first order. B is second order. Again, just looking at the axis title. And then C is third order. Those correspond to the left side of the integrated rate laws, right? That's all there is to it. Now they want us to solve for the initial concentration. So when you're solving for the initial concentration, this is when T equals 0, right? So what we can do is in this case, T is equal to X, right? It's just on the X-axis. So we're going to plug in 0 for X. Now, this is not just that cut and dry. Let's start with the 0th order. Why did I write third order? I said 0 and I wrote third for a second third. Starting with the 0th order rate law, plugging in 0 for X in this line, right? Just in Y equals that. If I plug in 0 here, and let me actually plug in 0 for X in line of best fit equation, which is just these line equations. If I plug in 0 for X here, I get 20, right? Now, that's true. I do want to note here is that all the Y values, so please note this, the Y values are equal to the axis titling. So in other words, for C, for the 0th order, when you're plugging in 0, that's the initial concentration. Right? This is equal to 20 from our formula, just looking at the axis, right? Now, when we go to first order, please keep this in mind, right? Because it's not the same. For the first order, if you plug in 0, you get 0.69. The initial concentration is not 0.69. You would be wrong, right? When you're plugging in that initial concentration, think of this as a function of time. This is the initial concentration, ln of the initial concentration here is equal to 0.69. ln of the initial concentration is 0.69, not the initial concentration. So you have to solve for the initial concentration, which you just do e to the power of both sides, or exponentiate both sides. And so e to the 0.69, which is about equal to 2, apparently. Moving on to the second order, please make sure your y's are plugged in appropriately, right? Y in this case is equal to 1 over b. So 1 over the concentration of B, or the initial amount of B, is equal to 10, which means that the concentration of B is 1 over 10, or 0.1. So please keep these in mind, right? When you're reading the graphs, make sure you don't just plug in. Don't just plug in 0 and be done with it. This one says choose the incorrect answer. So we're getting the kinetic theory. It says the rate of a chemical reaction A usually is increased when the concentration of one of the reactants is increased. This is true generally, not always true, but very usually that's the case. When you increase the concentration, there's just more of that molecule to collide with stuff. So yeah, usually the rate of reaction increases. B, it says is dependent on temperature. That is true too. The higher the temperature, the more collisions you have, or the easier it is for something to decompose. So it is dependent on temperature. C, the higher the temperature, the faster the rate of the reaction is. C, it says may be increased by certain catalytic agents. That's true, right? D, it says will be very rapid if the activation energy is large. That's incorrect. If the activation energy is large, this is going to be slower. Larger activation energy means slower rate of reaction, right? You need a higher amount of energy to just get the reaction going, or for the reaction to happen. And then E says describes the change in the concentration of a reactant or product with time. That's true. So we can't really, so that it's just D in this one. Large activation energy, slower reaction. Next, it says, by inspection of the reaction profile for the reaction A to D given below, answer the following questions. How many intermediates are there in the reaction? How many transition states are there in the reaction? Okay, so we'll just go one at a time. So how many intermediates are there? Intermediates are things that you have in the middle of the reaction. So they're not at the ends. That's a reactant. That's a product. Reactant is here. Product is here. So the intermediates are the things that form in between. They're in these low wells, right? Because they actually form kind of like a metastable chemical. But the intermediates form in between in those wells, right? That's where they are on the reaction coordinate. So how many intermediates? We have these two wells. So the answer is just 2, very simply. How many transition states are there? You're just counting the number of bumps going up. So that's 3 transition states. It has to go from reactants to B. So A to B, that's 1. B to C is 2. C to D is 3. Transitions 3 times. So there's 3 transition states. Which is the fastest step in this reaction? So this one you have to look at which one has the smallest activation energy, which ends up being C to D. Smallest activation energy. That's it. So faster, your smaller activation energy is faster step. D, it says which step has the smallest rate constant, or which one is the slowest. That one is B to C. This one is highest activation energy. E says, is the first step of the reaction exothermic or endothermic? Well, endothermic, just as a reminder from 2A, endothermic reactions go from reactant to product. It goes up in energy. It's absorbing energy. So this is endothermic. The overall reaction, having everything in here, right, from reactant to product at the end, this ends up being exothermic because the reactant is higher in potential energy than the product. Right, so this is A to B. A to B absorbs energy. And then from here, overall, A to D releases energy. The potential energy is decreasing. Next is according to thermodynamics, the transformation from diamond to graphite is spontaneous. Um, diamond to graphite has that delta G value in kilojoules per mole, but we never really see it happen. Estimate the rate constant and half-life, assuming its first order, of this reaction with a pre-exponential factor of A is equal to 1, and the activation energy is 540 kilojoules per mole at 298 Kelvin. Approximate age of the sun, approximate age of the universe. So we need neither of those last ones. I'm not sure they're thrown in, probably just fun facts. Um, what we can do is this. So the rate constant, you have a formula for it. It's K is equal to A times E to the negative EART. It's a little bit, I don't like the tiny fraction, so I'm going to write this as just EXP. It says negative EA over RT. All I got to do is plug this in. This is very straightforward once you have this formula. So A is 1. You're taking E to the power negative 540. Now, something you do have to do is this convert this to joules, not in kilojoules. So this is 540 times 10 to the third joules. Divided by, and the reason it's in joules is because you're using your energetic constant, 8.314. This is in joules per mole Kelvin, right? So the joules have to cancel out. We're at 298 Kelvin, like that. And then, oops, we end up getting, when you plug this in, 2.23 times 10 to the negative 95 inverse seconds. So it's very, very small. Very small. Right, and then when you calculate the half-life, we have ln of 2 divided by k. So finding the half-life here, we're just plugging in k. Oops, negative 95, 3.1 times 10 to the 94th seconds when you plug it in. So it takes a while. Oh, so this is where the things come in here. It's about like 10 to the 10th power or something, right? Longer than times the age of the universe, in terms of time. That's very long. Very, very, very long. Um, which is why you don't see it happen. It's due to the high activation energy. Next, it says we have a rate constant for this reaction. It has been determined at the following temperatures: 599 Kelvin, K is equal to that, 683 Kelvin, K is equal to that. We need to calculate the activation energy for this reaction. So this is a formula that you should have. So for A, the formula you should have is ln of K1 over K2 is equal to the activation energy over R times 1 over T2 minus 1 over T1. If you're wondering where this comes from, you just plug in two different temperatures in the equation we just used before in this Arrhenius equation. Two different temperatures with the same activation energy with two different Ks, and you're just dividing them. That's all it is. The A cancels out. You take the ln to get rid of the E, and then you simplify. But it is just a division here. Um, nothing else fancy. That's where it comes from. So when you do this, you can plug it in. We have the K values. 5.4 times 10 to the negative fourth divided by 2.8 times 10 to the negative 2 equals the activation energy, which we want to look for. R is 8.314. I'm not going to put in the units just to keep this a little bit cleaner. I'm going to move this over. Our first temperature, 683. Or whoops, sorry, our second temperature. Yeah, our second temperature, my bad. Right, corresponds to this 2.8. That's our K2. Minus 1 over 599. And then you solve for EA. So solving for EA here. Again, you're just doing a little bit of algebra. So 5.4 times 10 to the negative fourth, 2.8 times 10 to the negative 2. You can simplify this fraction if you want. I'm just going to leave it in. Divide by that. 1 over 683. 1 over 599, because it's multiplying by the activation energy. And then all of this times, or on the top, 8.314. Now you go ahead and just plug into your calculator, and you get 1.6 times 10 to the fifth. This is in units of joules per mole, right? Activation energy in this equation is in joules per mole. Or you can say it's 160 kilojoules per mole, doing the conversion. And that's it. That's it for A. Then B says, at what temperature will the rate constant for the reaction have the value K is equal to 5 times 10 to the third? So once again, you're using the same equation, right? You can plug in your K's and your T's, and you're solving for a temperature. So ln K1, let's just say that that's the one that we're looking for the associated temperature with. 2.5 times 10 to the negative third. Let's use one of our other k's. I'm just going to keep it the same as before. One on the bottom. 2.8 times 10 to the negative 2 is equal to, we have EA, that's 1.6 times 10 to the negative fifth. R is 8.314. This is 1 over 683 for the second temperature. I want to find the temperature that is associated with that top one, top K value. And then you just solve for T here. So solving for T here, you can multiply both sides by the reciprocal of 1.6 times 10 to the negative fifth, right, over 8.314. So this is times 8.314, or 1.6 times 10 to the negative fifth. Then you subtract out the 1 over 683. This has a negative, so you have to get rid of the negative. You multiply this whole thing by a negative. This is equal to 1 over T. When you plug this in, you get 1 over T is equal to 1.55 times 10 to the negative third. Then you can go ahead, cross multiply, divide, and you get T is equal to 645 Kelvin. And that's it. So a lot of these are just plug and chug if you have the formulas. It's a lot of algebra. So make sure you know your log rules. Make sure you understand how to manipulate the expression. But if you know that, then you should be fine. Next, it says derive the rate law for the iodide hypochlorite reaction. Hint, what would the concentration of H2O liquid be throughout the reaction? So first, let's write the rate law for this reaction. So the rate law is based on the slow step for these three reactions, right? So the rate here is equal to K times the concentration of iodide times the concentration of HOCl. This HOCl is not found in this reaction, right? So it's not going to occur in our rate law. So we need to get rid of or substitute HOCl. So what do? Well, looking at one of these other reactions, which one has HOCl or your hypochlorite? The top one does. So fairly simply, what we can do is write the rate law for that. We can say this one's the overall rate. Then looking at this one, we can say the forwards rate is going to be equal to OCl minus times the concentration of H2O, which we'll talk about in a second. It is a liquid, times K, K1. Now, this doesn't really help, right? Because I want to get rid of HOCl minus, but what can I do? So we can write the backwards rate like this. Backwards. I'm going to say that this is a rate constant of K negative 1. So it's for the first reaction. And it's going backwards, right? It's not the same as K1 to the negative 1. It's not the same. Like from 2A, you're reversing stuff. This is just a backwards constant for the first reaction. I don't know what it is. It's not the first one inverted. This is equal to the concentration of hypochlorite or hypochloric acid, sorry, times the concentration of OH minus, like that. Solving for, so now something you can note is assuming equilibrium. Then you can say the forwards rate is equal to the backwards rate. Right? That is the definition of our equilibrium. So if you're at equilibrium, then you know that the forwards rate, which is K1 times the concentration of the hypochlorite ion times the concentration of water is equal to the backwards rate constant times hypochloric acid times this OH minus. Then you can solve for the concentration of the hypochloric acid just by algebra. And we end up getting K1 times, forgot, OCl minus times the concentration of water divided by the concentration of hydroxide. And then we have a K -1 down here, right? The backwards one. So this is just by algebra. And then this one is a consequence of assuming equilibrium. And all you have to do is plug this in. So now we're going to plug in. I guess it wasn't there. It was over here. So we get rate is equal to K. And this is, yeah, K for the overall reaction times the concentration of iodide times that big thing, K1 times OCl minus times concentration of water, K -1, concentration of hydroxide. And actually, I do want to note here, this K is the rate determining K, right, for the overall reaction. However, it's more appropriate here to say K2 because it's determined by that second rate constant, whatever that is. You go ahead and you just multiply it out, essentially. Oops. So lumping all my equilibrium constants and the water. Then we end up getting this. So this whole thing we're going to say is K, and the water is 1 because it's a liquid. So we don't really consider it. And then these things we're going to lump together as K. So this is K times the concentration of OCl minus times the concentration of iodide over hydroxide. Would you look at that? That's what we got on page 2 with that data table. Then this is it, right? So your rate law is going to contain this one. And maybe I should have done this in the beginning, but you know the rate law is going to contain something like this. It's going to be K times OCl minus to some power times iodine to some power times OH to some power. And then you can use these different reactions to figure out what it is and their rate constants. Okay. Moving on. It says the following three-step mechanism has been proposed for the reaction of chlorine and chloroform. The numerical values of the rate constants for these steps are that derive the rate law and the magnitude of K for the overall reaction. So we know here that K2 is smallest. So that means it's the rate determining step. So when we write this rate law, you can say rate is equal to K2 times the concentration of chlorine times the concentration of chloroform, like that, right? From this one. Now, do note here that the chlorine is not what we want, right? Because what we're looking for in this overall reaction, chlorine and chloroform, we're looking for something where the rate is equal to K times the concentration of chlorine to some power times the concentration of chloroform to some power. So what we need to do, just as we did before, is substitute the concentration of chlorine because it's not in the rate law we want, right? The overall rate. So we can get this from the first one right up here. I'm just going to do what I did before. Um, Assuming equilibrium, you can say that forwards and backwards rate are the same. And we can set these equal to each other. So the forwards rate is K1 times the concentration of Cl2. The backwards rate is equal to K negative 1 times the concentration of Cl squared because of the 2, right, coefficient. So solving for the concentration of Cl, because I want to substitute it, K1 divided by K negative 1 times Cl2. This is all to the 1/2 power, or taking a square root. 1/2 power just looks nicer, so I'm going to leave it like that. Then we substitute. Substituting this into what we just had over here gives us rate is equal to K2 times chloroform. We're allowed to move things around, right? Associativity, or sorry, commutativity of multiplication. The Cl is K1 divided by K negative 1 times Cl2 to the 1/2 power, right? Now they want us to calculate what the magnitude of K is for their overall reaction. So they just want K. This is what we want. So what you can do is go ahead and distribute that 1/2 power just using your typical power rules. This is K1. You can write K1 to the 1/2 over K negative 1 to the 1/2. This is going to be a little bit cleaner. Cl2 to the 1/2. Then you can clump the K's together, just like we did before. This is K, right? Because if you look at these, This is the overall rate law. It has the same form as this. You have a K. You have Cl2 to some power. You have Cl3 to some power. The power is 1. So then you just get to plug in for K here, right? Pretty simple. K2, they tell us, is 1.3 times 10 to the negative 2. K1 is 4.8 times 10 to the third. K negative 1 is 3.6 times 10 to the third. That's the 1/2. You plug this in and you get 0.015. And that is it for this problem. So again, when you find the overall rate law, any of those k's you clump together, that is the overall rate constant. Next says, one proposed mechanism for the formation of double helix in DNA is given by the following reactions, where S1 and S2 represent strand 1 and 2, and S1 colon S2 star represents an unstable helix. Write the rate of reaction for the formation of a double helix. So in this problem, we don't know which one is the slow step, right? You're not explicitly given any K values. I can tell you which one's probably the slow step, but you can't use what we've been doing a second ago, right? Before we were basing the slow step off the K values, or they just told us. Can't do that here. We can't write stuff. However, what we can do is use the pseudo steady state hypothesis, where the rate of the intermediate, or the rate of this, actually, let's make it general. The rate of the intermediate is equal to the rate and, sorry, formation of the intermediate. Rate of formation is equal to rate of disappearance. So why does this work here? You form this unstable double helix in the middle, right? It's the intermediate of this reaction. Since it's an unstable intermediate, we get to use this. We can use it because it is an unstable intermediate, right? We're talking about the unstable helix. This means it's short-lived. So as quickly as it forms, it just as quickly disappears. If you want to think about in terms of energetics, it forms and it's very unstable. It doesn't like being like that. So it reacts very quickly to either go back to what it was or something else. But things that are very reactive are going to be very short-lived. This is pretty much always true. So using this hypothesis, what we can say is the rate of formation of the intermediate, which is the forwards reaction, right? K1 times the concentration of S1 to the first power, concentration of S2 to the first power. This is again, rate of formation is equal to the rate of disappearance. So the rate of disappearance, there's two things that can happen. It's going to be the rate that it goes backwards, right? So it says, I didn't like this. I don't want to do anything else. I'm going to go back to being S1 and S2. So it's this thing. These are in parentheses. There's a star here, right? That's the rate from the first reaction. But there's two rates, right? Because we're going to have to add these up. The first rate is it going back from this first reaction, saying, I don't like this. I'm just going to go back. The other thing that can happen is that it moves forward and forms the stable double helix. So you have that first rate of disappearance going backwards. You also have the rate going forwards, right? It's still disappearing. You're still using it up to react in both of these. But you have to add those rates up, right? If I have two different places where it's being used at different rates, you just add them up. It's just a combination. So then I can say this is plus K2 times this unstable intermediate. Like that. Right? This is the rate of disappearance. This is the backwards reaction from the first one. This one is the forwards reaction from the second one. Okay. Um, and then it says write the rate of reaction expression for the formation. Okay. So we have this expression. Now we have to do a little bit of algebra here. We want to figure out what the concentration is of this intermediate. So the concentration of this intermediate, doing a little bit of algebra. S1, S2. We get, so you're factoring these out from the K1, K minus 1, and K2, right? So something like this. K minus 1 plus K2, right? Then you divide both sides by K minus 1 plus K2. Concentration of S2 over K minus 1 plus K2. So now we have this. And then we just write the rate, right? So the rate for the formation of the double helix this is equal to the concentration of this unstable intermediate times the second rate constant. So that's just the rate law for the second one. That's all it is. And now since I don't have or since now I have the concentration of that intermediate, I get to plug that in. So K2 times K1 times these two concentrations like that. And then that is it. There are two cases where you can say rate 1 is the rate determining step. If rate 1 is the rate determining step, you'll know that K2 is going to be much bigger than K1 and the inverse reaction, right? Bigger K means it's faster. So you're saying K2 is a lot faster, right? K1 has to be rate determining step. You can plug in a few limits here. You end up getting, it reduces down to K1 on the top, and then everything else disappears. Everything else vanishes because the bottom you're left with just K2, right? It's a lot bigger than K minus 1. So the K2 on the top and bottom cancel out. If the second step is the rate determining step, then you know that K1 and K minus 1 are a lot bigger than K2. So you get K2 times K1 on the top, and then you divide by K minus 1 because adding something small, the K2, to K minus 1 gives you about the same thing. Those I will not write out. I don't think that's super important, but I think that's kind of cool that you can kind of, I don't want to say guess, but you can assume one is the rate determining step and then find two expressions for that. But this is the overall rate. not knowing which one is the rate determining step. Last one, it says the following mechanism can be used to account for the change in apparent order of unimolecular reactions, such as conversion of cyclopropane A to propane P, or propene, sorry, P, where A star is an energetic form of cyclopropane that can either react or return to the unreacted cyclopropane. So if A plus A can turn to A star plus A, and then A star can turn into P. Show that low pressures of cyclopropane, the rate law is second order in A, and at high pressures, it is first order in A. Once again, we have an unstable intermediate. So you can assume we're going to use the same thing here. We're going to use the pseudo-steady state hypothesis because we have an unstable intermediate. So in other words, the rate of formation of A star is equal to rate of consumption or disappearance, appearance, it doesn't really matter. They're all synonyms, right? Writing these two rates in, the rate of formation of A star is just based on this first rate law. That is going to be K1 times the concentration of A squared, where it's two A's, right? A times A, that's going to be A squared. The rate of consumption of A star, maybe I should write this closer to the equal sign, just to make this really clear, is the second one plus the first going backwards. So the first one going backwards is K minus 1 times the concentration of A times the concentration of A star plus K2 times the concentration, or yeah, just A star. So once again, this one is this reaction going backwards. That's one way A star gets consumed, plus the rate that it gets consumed and forms P. That's the other way. You can just add up the rates. You solve for the concentration of A star here. Doing a little bit of algebra. All right, you factor out the A star from the right, and then you just divide. I'm not going to write that out. We have K, this is a minus 1, A plus K2. Again, I just factored out A star from the right side because they're all multiplying. It's in both. Then I divided by K minus 1 over A plus K2. So this is the concentration of A star. Now the rate I am interested in is how P forms. So I want to know how P forms. That is going to be the concentration of A star times K2. And then you can just plug it in, K2, and then this is K1. So I'm just substituting that thing. Times the concentration of A squared, K minus 1, concentration of A plus K2. All right. So then that is for the rate of formation of P. So now we have to look at the low pressure and high pressure part. Like, what does that mean? So remember from 2A that you talked about gases and the ideal gas law and stuff? the concentration of A, and actually it's the other way around. Sorry. The pressure in the system is dependent on concentration of A, right? The higher the concentration of A is, the higher the pressure. The lower the concentration of A is, the lower the pressure, right? It's just dependent on moles of gas. Recall that from 2A. So when you're looking at this, and the terms that you're really looking to cancel out, right, is terms where you are adding and subtracting things. Things that you're multiplying doesn't really make sense. You can't make a comparison and say one is a lot bigger than the other, right? If it doesn't matter. You still multiply them out. Where we are kind of simplifying things or making things go away is where you see addition or subtraction. In this case, we have addition in the denominator, right? And so if one term is a lot bigger than the other, then adding the small term is basically going to not change it, right? If you add 1 times 10 to the negative 10th to 10, it's basically 10. It's not actually 10, but it's basically 10. So at a low pressure, and the terms we're looking at again is these bottom terms, this K minus 1 times the concentration of A plus K2. We're not even looking at the K's here. We're really looking at concentration of A based on this pressure. So at a low pressure, we know that K1 times A is probably going to be a lot smaller than K2, right? And this is because the concentration of A is small. We're kind of talking in extremes here, right? Because we don't know what K2 is or K minus 1. But assume at really low pressures. We know A, and it's because A is small. So we know A is going to be small at low pressures because there's less moles of gas. So the rate simplifies to K1 A1 squared or K minus 1A, like that. Well, oops. No, I messed that up. Totally messed that up. Over K2, my bad. Like that. I don't know why I put the concentration. You can see here this is second order. Because it's squared here. Also, I do want to note, right? You're like, well, where did I get that? K minus 1A disappeared. Again, if this is true, then K minus 1 times A plus K2 is really about equal to K2, right? Just about. At a high pressure, we're doing the same thing, except the other way around. So the concentration of A times the inverse reaction is going to be much bigger than K2. This is because the concentration is large. So the K2 essentially vanishes. K1, K1 squared, and this is K minus 1 times the concentration of A. Now you can note that one of the A's cancel out. You get K1, K minus 1 times A. And this is first order because A is to the first power. And then that is it. All right, I hope this video helps, and I will see you in the next one.